Hello everyone. I'm Takayuki Shinohara of Tokyo Institute of Technology. I'm very pleased to have this opportunity to talk image-to-point cloud translation using conditional generative adversarial network for airborne LiDAR data. I'm going to divide my presentation into 4 parts. First, I will talk about background and objective of our research. Second, I will show our proposed image-to-point cloud translation method. And then, I will talk about experimental result to evaluate our method. Finally, I will show the conclusion of our research and future studies. Let me begin by introducing the background and objectives. First of all, I will show the image-to-point cloud translation task. Image-to-point cloud translation aims to estimate the point cloud with x, y, and z coordinate corresponding to the input aerial photo. 3D reconstruction using image are widely used in various fields. Most of 3D reconstruction methods are focused on multi-view image-based methods. Recently, deep learning-based 3D reconstruction from single image have been studied. Deep learning is important for 3D reconstruction from single images to achieve low-cost 3D restoration. Here, I will talk deep learning-based 3D reconstruction from single image. In the computer vision domain, generative adversarial networks are widely used for image translation tasks. A method for converting aerial photo to height images using image translation was proposed. However, since the output is in the form of an image, the 3D detailed structure cannot be reconstructed. Therefore, point clouds reconstruction from images is needed. Here, I will talk about single image point cloud reconstruction. Most of previous studies focused on single object reconstruction from an image. Therefore, it is not applicable to cases where multiple objects are captured, such as aerial photo. I will introduce the deep learning methods needed to achieve 3D reconstruction of complex single images. The first method is image transformation. Pix2Pix achieved stable image translation by using conditional GUN. The second one is an auto-encoder for point clouds. FoldingNet is the one of the famous auto-encoder method for point cloud. FoldingNet has a method that uses a two-dimensional grid as the initial value and a decoder to recover the point cloud. Therefore this method can extend to create a point cloud by input images. We propose Pix2Pix like aerial photo to airborne point cloud translation with FoldingNet like generator. Next, I will talk about our proposed method. Now, I'd like to show the overview of our proposed method. Our network consists of translation and GUN. Translation uses 2 networks, encoder and generator. The encoder maps input image into latent feature Z. The generator reconstructs fake point cloud from latent feature from the encoder. Additionally, we use GUN-like discriminator to judge the reconstructed fake data by the generator or randomly sampled from real point cloud data. The discriminator leads to a realistic and clear generated point cloud. I will talk about the encoder. The encoder is based on ResNet. The ResNet-based encoder extracts latent feature from input image. Next, I will talk about the generator. The generator is based on FoldingNet. The FoldingNet-based generator reconstructs point cloud from latent vector from the encoder. In the generating process, the generator gradually transforms the latent vector into point cloud. Additionally, after each MLP, we concatenate image feature and 2D grid. Next, I will explain the point discriminator. The point discriminator is based on PointNet++, and is fed with fake data colored by the generator or real data. Point discriminator judges whether the input data is real or fake. Here, I will introduce the optimization of our network. In the optimization process, we use 2 types of loss function according to reconstruction and GUN. The first one is reconstruction loss. The reconstruction loss calculates the distance between generated fake data and real data. As this distance, we use chamfer distance and earth mover distance. Generally, these distances are used for calculating the difference between 2 sets. The second one is GUN loss. We use Wasserstein loss. In the actual training process, we use all these objective functions. Here, I will talk about experimental results for the evaluation of our method. For this experiment, we used GRSS Data Fusion Contest 2018 data including aerial photo and point cloud. The target area is an urban area as shown in the upper figure. This area contains buildings, vegetation, roads, and so on. For training our model, we split aerial photo and point cloud into small patches from the original large point clouds due to limitation of GPU memory. We define the patch size as 25 square meters. Additionally, we subsample into the same number of points in each patch. Here, I will introduce the translated point cloud from input point via our generator. We show some typical results including buildings, vegetation, and car. The left figures indicated input image as condition for generator. The middle figures indicate our translated results from generator. The right figures indicate ground truth point cloud corresponding to input image. Finally, I will show the conclusion and future work. For the conclusion, we propose a generative model for point cloud observed by airborne LiDAR using PIX2 PIX-like conditional GON pipeline. Our trained FoldingNet-like generator was able to make fake point clouds clearly from input image. For future work, we only evaluate generated point cloud qualitatively, so we must find a way to do quantitative analysis. And, our model can only generate 2048 points, so we should also find a way to generate denser point clouds. Moreover, we have used a traditional generator, so for future work we will use more recent powerful transformer-like generators. Thank you for listening.